let's say that something is traveling at a constant rate of 5 meters per second. That's its velocity in one dimension. If it was negative, it would be moving to the left. If it's positive, it's moving to the right. And let's say that we care about what is our change in distance over, the delta symbol represents change, over a change in time of 4 seconds. Over 4 seconds. And I could say from t equals 0 to t is equal to 4. That's our change in time. That's our 4-second interval that we care about. Well, one way to think about it is, well, a rate by definition is nothing but a change in some quantity, in this case it's distance, over a change in some other quantity. In this case, we're thinking about time. Or another way to think about it, if we multiply both sides times change in time, you get your change in distance is equal to your rate times change in time. Rate times change in time. And so this is very close to, you might remember from pre-algebra, distance is equal to rate times time. And that just comes from the definition of what a rate is. It's a change in one quantity with respect to another quantity. And so if you just apply this, if you say, okay, my rate is a constant 5 meters per second, and my delta t is 4 seconds, so times 4 seconds, well, that's just going to give you 20. That's just going to get you 20. Let me do that same color that I had for the change in distance. That's going to be 20, and then the seconds cancel with seconds, 20 meters. So my total change in distance over those 4 seconds is going to be 20 meters. Nothing new here, nothing too fancy. What I want to do now is connect this to the area under the rate function over this time period. So let's graph that. Let's graph it. So that's my rate axis. This is my time axis. This is going to be in seconds. This is going to be in meters per second. So let's see, 1, 2, 3, 4, 5. That seems about enough. And then I go 1, 2, 3, 4, 5. Our rate, at least in this example, is a constant 5 meters per second. It's a constant 5 meters per second. So that is my r of t in this example. And so what did we just do here? We just multiplied our change in time times our constant rate. We just multiplied our change in time. So it was from time equals 0 seconds to 4 seconds. So it's this length here, if we think of it on that axis. And we multiplied it times our constant rate. We multiplied it times this right over here. But if I multiply this base times this height, what am I going to get? I'm going to get the area under, I am going to get this area under the rate function. And that area is going to be 20. And if we went with the units of them, obviously you're used to things of area being something, unit squared, because it's usually, meters times meters, or miles times miles, or inches times inches. So it'd be inches squared, meters squared, or miles squared. But here, if we go with the units of the axes, it would be meters per second times seconds, which is going to get you meters. But the important thing here is that the units here, or the area here, is 20. So at least for that very simple example, it looks like the area under the rate curve is equal to the net change over that time period, where the rate is something with respect, where we're saying that it's the rate of something with respect to time. But let's test that a little more. Let's just get a little bit more intuition here. Let's say that we had a different rate function. Let's say that, let me make it with a different, let's say instead we had a rate function. I'll still use yellow. Let's say I have a rate function that is, let me make it a little bit interesting. Let's say it's 1 meter per second for time is greater than or equal to, or 0 is less than or equal to time, which is less than or equal to 2 seconds. And this is obviously, this is all in seconds where we're talking about time. And there's 2 meters per second for t is greater than 2 seconds. So what's that going to look like? And actually, try to graph it yourself and just say, well, what is the total change in distance over the first, let's say, 5 seconds? So we want to do delta t over not the first 4 seconds, but the first 5 seconds. Well, let's graph it. Let's graph it. So this is 1 meter per second. 1 meter per second, that is 2 meters per second. It's in meters per second. That's my rate axis. And this right over there is going to be that's going to be my time axis. 1, they're obviously not at the same scale. 3, 4, 5. And what does this rate function look like? Well, my rate is 1 meter per second between time is 0 and 2, including 2 seconds. And then the rate jumps. And this isn't that realistic. Nothing can accelerate instantly like this. You would need an infinite force or an infinitely small mass, I guess, to, well, maybe there's some things if we think about, well, anyway, I don't want to get too complex there, but this is unrealistic. It's not typical for something to just have an instantaneous velocity increase like that. But let's just go with it. So then after the 2 seconds, we are at a constant rate of 2 meters per second. Now, what is our total change in distance over the first 5 seconds here? So here we care about the first 5 seconds. Well, we can break up the problem. We could say, well, over the first 2 seconds, change in time is 2 seconds times we have a constant rate over those 2 seconds. So it's going to be 2 seconds times 1 meter per second. Well, that's going to give us 2 meters. So this here is going to be, actually, let me do that orange color. That's going to give us 2 meters there. And then we look at the next section. Our change in time here is 3 seconds. And then we multiply that times our constant 2 meters per second. That's going to give us an area of 6. And if we look at the units, in both cases, we're multiplying seconds times meters per second, which is going to give us meters. So it's going to be 2 plus 6 meters, or 8 meters. So hopefully this is giving you the intuition that the area under the rate curve or the rate function is going to give you our total net change in whatever that rate thing was finding the rate of. In this case, it is distance per unit time. If you take the area under the rate function, that kind of distance per this speed or this velocity function over some period of time, that area is going to be our total net change in distance.